Hello students, now we will discuss the junction breakdown. When a sufficiently high field is applied to the PN junction, the junction breaks down and conducts a very large current. There are basically three breakdown mechanisms. First one is thermal instability. Thermal instability. The second one is tunneling effect and third one is avalanche multiplication. Second one is tunneling effect and third one is avalanche multiplication. So we will discuss these mechanisms one by one. So first one is thermal instability. Breakdown due to thermal instability is responsible for the maximum dielectric strength in most of the insulators at room temperature and is also a major effect in semiconductor with relatively small band gap like germanium. Because of heat dissipation caused by reverse current at high reverse voltage, the junction temperature increases. This increase in temperature in turn increases reverse current in comparison with the value at the lower voltages. The temperature effect on reverse IV characteristic is as shown in this figure. So this figure, that is figure 1, shows the effect of reverse current on the IV characteristic. Each line represents current at the constant junction temperature. The heat dissipation curves are proportional to the IV product are shown as straight line in the plot. These lines correspond to curves of constant junction temperature. The reverse current voltage characteristic of the junction is obtained by joining the intersection point of the curve. Here are join the intersection points of the curve, which gives the reverse current voltage characteristics. Because of heat dissipation at high reverse voltage characteristic shows a negative differential resistance. In this case, the diode will be destroyed unless some special measure like large series limiting resistor is used, and this effect is called thermal instability. The voltage VU is called turnover voltage. This is the voltage VU, which is called turnover voltage, and for PN junctions with relatively large saturation currents, the thermal instability is important at room temperature. However, the thermal instability becomes less important compared with the other mechanisms. Then the second one is tunneling effect. It is well known that for a one-dimensional square energy barrier with barrier height E0 and thickness W, the quantum mechanical transmission probability TL is given by TL is equal to 1 plus E0 square plus sine hyperbolic square of K into W upon 4E into E0 minus E raised to minus 1. So this is equation number 1, which gives the transmission probability, where the K is equal to this small k is equal to under root of twice m into E0 minus E upon h cross square. Where E is the energy of carrier. The probability decreases monotonically with decreasing energy when K into W is greater than 1. The probability becomes, that is this transmission probability, which is nearly equal to 16E into E0 minus E upon E0 square into exponential of minus 2k into W. So this is next equation number 2. A similar expression has been obtained for PN junctions. The tunneling current density is given by JT is equal to under root twice m star into q cube into epsilon into v upon 4 pi square into h cross square into Eg raised to 1/2 into exponential of minus 4 into under root twice m star into Eg raised to 3/2 upon 3q epsilon h cross. So this is equation number 3, where this epsilon is the electric field. Eg is band gap. V is applied voltage. And m star is effective mass. When a field approaches to 10⁶ volt per centimeter in germanium and silicon, significant current begins to flow by means of band-to-band tunneling process. To obtain such a high field, the junction must have relatively high impurity concentrations on both, that is P and N sides. The mechanism of breakdown silicon and germanium junctions with breakdown voltages less than about 4 Eg/Q is found to be due to tunneling effect. For junctions with breakdown voltages in excess of 6 Eg/Q, the mechanism caused by avalanche multiplication. At voltages between 4 to 6 Eg/Q, the breakdown is due to mixture of both, that is avalanche multiplication and tunneling effect. Since energy band gap Eg in germanium, silicon and gallium arsenide decreases with increasing temperature, the breakdown voltage in these semiconductors due to tunneling effect has a negative temperature coefficient. That is, the voltage decreases with temperature. This is because a given breakdown current gel can be reached at smaller reverse voltages at higher temperatures. A typical example of this is given in this figure number 2, which gives the breakdown voltages in different at different temperatures, and the temperature effect is generally used to distinguish the tunneling mechanism from avalanche mechanism, which has positive temperature coefficient. That is, breakdown voltages increases with increasing temperature. So, in next lecture we will discuss the avalanche multiplication process. So, with this I conclude this lecture. Thank you.